Okay, welcome back everyone. So we are very happy to have Marc Bellemare to start this afternoon session, who is going to tell us about the distributional perspective on reinforcement learning.
All right. Yes, thank you for the introduction. This is work that's been going on for about a year and a half and still ongoing. And if there's one question you should remember from this talk, it's the following question. Why does it work that way? And you'll see, as I explain the main concepts, that there's still a big gap between the theory and the practice. Okay, so let me actually start with the basics of reinforcement learning. In reinforcement learning, we often model the world in a Markov decision process with a policy which maps states through distributional actions. Okay. And then we have a reward function R, a transition function P, and a discount factor. And then we look at this policy, and we can actually write the transition function as P pi, which is the probability from moving from state X to X pi. And for most of the talk, I'll actually just write things down with P pi and R pi, the expected reward, and the actions will come in only when we talk about choosing the optimal policy. Okay, so we have this policy. Now the value function attached to this policy is the expected sum of discounted rewards that we expect to get as we follow this policy through the MPP. Okay? Starting in a state X and sampling states according to this transition function P. And now, of course, there's a value function, and we know we can write a value function in a very concise form using Bellman's equation, which is a value function at X is equal to the expected reward plus the discounted next state value. So that's good. Now, when we actually want to maximize the sum of rewards, we're now going to look for a policy maximizing this value function. Okay? And we know that there's a unique optimal value function Q star. And now I'm going to talk about state action values. And Q star says if I take action A from state X, I'll receive an expected reward, E of RXA. And then I transition to the next state. The only thing that changes with this equation compared to the previous one is we'll place the expectation under pi by a maximum over the actions. And then there's an optimal policy or multiple optimal policies that are going to be greedy with respect to Q star. And then implicit in all of this, if you're familiar with decision making, is that there's actually a stationary policy, but it only depends on the state and not on a time step. Right. So how do we actually go about learning this value function? Well, there's ways to model this learning process. The main way is to look at the Bellman operator. In vector form, the Bellman operator is going to take in a prediction, V, about the value function, and then back it up into a new guess. So it's going to be written T pi V, the operator applied to V, is equal to the reward plus the discounted expected next time. And same thing, we can do the same thing for the optimality operator, where we replace the fixed policy by the greedy policy with respect to our current guess Q. Okay. Now, the way we analyze learning in this setting is that the vanilla way to do it is to talk about the fact that they're both contraction operators in supremum norm with the contraction modulus of gamma. Okay, that's the discount factor. And what that means is, of course, if we iterate this process of applying the Bellman operator, then we converge to a V pi or V star. Okay. And these operators really form the basis of most stochastic update rules in reinforcement learning, where instead of seeing the whole distribution of next states, we just get a sample one and then apply our stochastic update with respect to this sample. So this would be the TD error, for example, would be the target, the one application of the Bellman operator minus our current guess. Now, yes, Joshua.
The V pi here is just the definition, or it's a particular value function?
So V pi would be for fixed policy. So I fix how I'm going to act in the world. And then the value of acting according to this policy would be defined as this expectation, which also is equal to this the solution of this Bellman equation. Okay. Let me show you this in a different way. with one of my favorite games, Monopoly. Okay? So if we want to apply reinforcement learning to the game of Monopoly, we're going to say we have a state, which is where the wheelbarrow is. Right? So, it's sitting on Park Place right now, and our opponent has hotels on Boardwalk and Park Place. And I'm going to roll the dice. That's going to be the stochastic element of the game. And then if I'm unlucky, I'm going to land on Boardwalk, lose $2,000. If I'm lucky, I'm going to pass Boardwalk and land on pass Go, receive $200. Okay. These are stochastic events. Now there's a state, as I said, there's a reward, and then the expected reward in this case would be just, we know how to do math, this would just be the average of the two rewards that we could receive. In this case, it's not clear in Monopoly whether there's a policy or if you're just throwing the die. Bear with me. Now, because this is actually a sequential decision-making process, we're going to repeat this process, maybe later making some decisions, so we get this whole tree of possible future with you. Okay. Now, what's funny is that we have this reward, right, which is really a random variable, so it's a sum of rewards, which are all random variables. And we have this Bellemare equation that defines the recurrence between these two things. Right? Now, the ground truth is that we have this tree of possibilities. But if you look at the Bellemare equation, right, which says the value of a fixed policy is the expected reward plus the expected next state value, the world looks a lot more like a flat expectation. Okay. Where at every step, you receive an expected reward, and you transition, in a sense, to a next state distribution over states, and you receive the next expected reward at this step. Okay. And this is fairly well known. There's been a number of works in literature comparing, especially in the case of linear approximation, comparing what happens if you learn an expected model versus actually modeling the real life. Okay. And another way to think of this implied model is that because, but by linearity of expectation, then we can actually really break down the value function into the expected reward of all these different time steps, just discounted by the right powers. Okay, so that's all fine. Now, if you look at this tree of possibilities, right, then each possible branch, each possible path through the MDP, you can think of it as a separate realization of this process. Okay? So we have the value function, which is an expectation of a sum of random variables. Well, what if we actually just look at that sum in and of itself as a single random variable? Right? So that's going to be the random return once we follow a random path through the MDP. And the value function is the expectation of that random return. So now the objective of this talk is to basically say we have the Bellemare equation, which relates on one side the expectation of a random variable to, on the other side, the expectation of a random return and a random next state. Random reward and random next state return. And so what happens if we informally knock out the expectation signs out of this equation? Okay. Well, it turns out that you can, in fact, write down a different kind of Bellemare equation, distributional Bellemare equation, which is going to say that the random variable is zi, which is the random return, and that's distributed like the random reward r plus the random next state. Okay. And so this was the basis of our HTML work last year. Okay. So what can we say about this equation? Well, let me give it a name first of all. So the collection of these random returns I'm going to call the value distribution. So that's the whole vector value, the mapping from states to distributions. Okay. And it has there's a solution to this equation. Okay. There's going to be a random variable that's distributed like the right-hand side. Okay. And the way to think of it pictorially is that you have a starting distribution over all these possible returns, which would be quite complicated. And then what this equation is saying is that you get a random reward, and then you get a random return next step, and all these sources of randomness come together to form the new distribution. Okay. And of course, this is not new. There's a laundry list of Bellemare equations you could write. So just for completeness, the regular Bellemare equation is the one for the mean of that distribution. There's also the Bellemare equation for the variance of that distribution, and so on. The novelty here is to really ask the question: what's the behavior of that whole collection and the whole distribution as a whole? Okay. So let me then outline the main three parts of this talk. First, I'll tell you about properties of this equation, okay, and how it relates to the regular reinforcement learning setting. And then I'll actually tell you how this translates into practical algorithms. Okay. And I'll come back with the optimality questions. So most of this talk is actually going to be about the policy evaluation setting where we fix the policy. Okay, so let's get started. There's a Bellemare operator which takes in a prediction V and then maps it to the expected reward plus the expected discounted next data. Okay. It turns out there is a distributional Bellemare operator which takes in a collection of random returns, a value distribution, and it maps it to a new distribution, new collection of distributions. Okay. And then the key here is that the sources of randomness, as I've said, are in the reward, the next state transition, and then the next state returns themselves. But that's a well-defined operator, and it looks like this. So the cartoon picture is you start with the next state distribution, and then when you apply gamma to that random variable, you're going to squash all the atoms of the distribution to make them closer to zero. Okay? And then you're going to shift it by the reward. Now that's a cartoon picture because, of course, p pi might lead to different states, in which case you're going to take the convolution with all these different states. And the reward itself, if it's a random reward, then again you take the convolution with respect to the random reward. But that's the cartoon picture. Okay. So what can we say about this operator? Well, first of all, as I was telling you earlier, when we measure the how the Bellemare operator over expected values behaves, we look at supremum norms. Okay. Now, what's a supremum norm of a distribution? That's not an obvious question. So let me start with a metric D, and the metric D is a metric between probability distributions. Okay, and so what we're going to do is take that metric D and try to build a metric which lets us analyze the distributional Bellemare operator. Okay. So first of all, I'm going to require that this metric D has three properties. Okay. First of all, I want it to be sum invariant. So if you give me two random variables, I'll apologize in advance. I'm going to mix up metrics over random variables and metrics over the distributions, and I hope you forgive me for that oversight. So two random variables u and v, okay, and if I add a third random variable a to both of these, and a is independent from u and v, then what I'd like d to be sum invariant, which means that the metric, once I add d, is no greater than, once I add a, is no greater than if I didn't add it. So that's the first property. Okay. The next property is what I'm going to call scale invariance, scale sensitive, which is that if I multiply both of my random variables by the same scalar value c, then I would like that c constant to come out of the metric. Okay. And I'm going to actually allow it to be exponentiated by a factor beta, and of course beta should be greater than 0, otherwise it's not scale sensitive. And then finally, the third requirement is that the metric be Jensen-like. Okay? And by that what I mean is that if I have a transition function, and I look at the random variable that results when I first sample a next state, and I look at the random return, okay, then we'd like to first of all be able to take out that p pi, but I'm actually going to require something slightly simpler, which is just that the distance between that random next return be bounded by the distance of the maximal return over the collection. Okay. So these are the three requirements we're making on this metric D. They're not actually too hard to satisfy, but they need to be there. So now once we have this is a metric between distributions. Now we have a collection of these, one for each state. So let's just do the simple thing of defining a maximal metric between two collections. So D bar is between Z1 and Z2, right? So think of it again as mappings between the two states, from states to distributions, and we'll just take the maximum value. So that's the part that looks like a supreme norm. Okay. Now once we have this, then it turns out that we can prove that the distributional Bellemare operator is in fact a gamma to the power beta contraction in the metric D bar. Yes, for sure.
What? I don't understand the right-hand side.
Sure. So the Z1 and Z2, you can think of them as collections. There's one for each state. There is a D missing. Thank you, Yeshua. There it is. Other questions? Okay, good. So that's going to give us our gamma to the beta contraction. And as we'll see in a second, that's not actually given. So once we have that, then we can appeal to Banach's fixed point theorem to say that there's a unique fixed point, Z pi, that satisfies this equation. So if you're familiar with the usual proofs in reinforcement learning, that's actually quite similar to what we normally do with this big step that we're actually choosing a metric B ahead of time, and then asking something with that metric. Yes, Java?
To apply Banach's fixed point theorem, you would need the completeness of the space.
Yes, and I was assuming that we're restricting it to the space of distributions of dynamic support and finite state spaces, but we can have a chat afterwards. Thank you. There's a D missing and also an assumption missing. Let me just walk you through the vanilla version of this proof. We have we're going to start with two predictions, Z1 and Z2, okay? And we're going to apply a Bellman operator to both of these. And I'm going to look at actually the value here in this case at one state x. Okay, so by definition, the distance between these two is going to be, I'm just expanding the definition of the operator P pi. So that's the distance between the reward plus the discounted next state return. Now, of course, these are random variables. So we're looking at the distance between the random variables or the distributions. Now, because we have this sum invariant property, right away we can knock out the random reward. Okay, so we end up with this next step. Okay. And because we have the scale sensitive property, we can take the gamma out. In this case, taking beta equals to 1. And then finally, because we have this Jensen-like property, we can take out the P pi. So it's very, very vanilla proof. And say relating the Bellman operator, the application of the Bellman operator to the next state. Okay. And this is, of course, this is d bar. So now if we take the supremum over the left-hand side of the top, we get d bar of t pi of z1 and t pi of z2, and that gives us the contraction we're looking for. And there's a gamma missing here as well. Okay. So fairly simple proof, but the three properties that I outlined are necessary for this. Okay. So which metric should we be using to actually compare, to look at how quickly we're converging to Z pi? Okay. So the natural one in machine learning is to look at the KL divergence. It turns out the KL divergence doesn't work for the very, very simple reason. First of all, it's not a metric, but even if it was, it's infinite if your supports are this one. Okay. And you really can't get around this issue because when you apply the Bellman operator once, you're likely to end up with a distribution that doesn't have the same support that you started with, unless you make much stronger assumptions. Okay. In fact, even if you have full support, it wouldn't be scale sensitive. Another one that's popular is a total variation, and actually there's a paper from 2010 that looked exactly at this idea of a similar operator and trying to measure how quickly you convert it in total variation. Now, it turns out that with total variation, you have this interesting issue that when you multiply your support by gamma, everything comes towards 0. But there's no reason, if the two supports were disjoint before, if you multiply by gamma, in general, they'll be still disjoint afterwards. So the total variation between them will still be 1, will still be the same. So again, if you look at things in terms of total variation, you don't have this scale-sensitive property, which is very interesting. So what do we do? It turns out that there are metrics that are scale sensitive. Okay? And one of them, a family of metrics that are scale sensitive, are the Wasserstein metrics. Okay? So one definition is to look at the integral from 0 to 1 of the inverse CDFs between two random variables u and v. Okay? And if you look at the Pth metric, then we would put the Pth power of the absolute difference between these two, and then take the P through afterwards. Okay. So the Wasserstein metrics have the properties we want. They're sum invariant, they're Jensen-like, and for all P, they're going to be scale sensitive with beta equals 1. So they'll give us a contraction of factor gamma. Okay. So what's the picture like? The picture looks like this. You can draw your 2 CDF, FU, and FV like this. So x would be the x-axis at the bottom, and then you have the y-axis ranges from 0 to 1. And when you integrate from 0 to 1, and you look at the absolute differences at every point, basically the area between the 2 CDFs, then you get the Wasserstein. Right? And if you squash them in a factor of p, then you get the Wasserstein p, and you exponentiate afterwards. So that's actually a very nice metric. Now another one that I'm going to talk about is the family of LP metrics. And the LP metrics actually integrate on the x-axis instead of the y-axis. And it might actually seem like a very, very trivial difference, but it will actually make a difference. And it turns out that the LP metrics will be submissing, making a face at me about the... Okay, then. You prefer the Wasserstein metrics?
Yes.
Okay, good. Then you'll appreciate the rest of the stuff. So if you integrate on the x-axis, so for p equals 1, they're the same as the W1. Otherwise, they're different. And in fact, they have the scale sensitive property, but with beta equals 1 with so in particular, if you take p equals infinity, you get the contour-rich measure, which is not scale sensitive. Okay, so it looks like this. As I said, you integrate over the x-axis. And one metric of particular interest is what's called sometimes the Kramer metric. The Kramer metric is that you're going to take the difference between the CDFs and then square it. Okay? And then that gives you the p equals 2 the case of the Kramer metric, and that thing has very special properties. Okay. So great. So these are some metrics we can use to analyze the distribution of that operator. Now, can we actually turn this into a stochastic update rule similar to TD learning? Well, it turns out you can. So if we look at TD learning, in TD learning we're given a state x, and we sample a reward and a next state. Okay? And then we define this TD error delta, and what we can say is that it converges to V pi under all the right conditions, Robbins-Monroe ergodicity. Okay? And one thing that's interesting is that this delta is sometimes called semi-gradient. It's not actually doing gradient descent over a loss function, but it is following a descent direction, so which is how you can show the convergence. Right? And so one thing you could say is if I fix my value at my next state and I don't allow it to be changed, if you will, by the gradient, then taking the gradient with respect to Vt of that would give me my TDR, my delta. So how does this matter in distributional RL? Well, first of all, let's look at the basic update. And let me define this concept of a push-forward measure. So in a push-forward measure, I'm just going to look at filtering a measure through all the atoms of a distribution through a function f. Okay? So in that case, what that means is you give me a distribution, and then I'm going to remap all the points that the distribution supports into f of x, f of z basically. Okay? So now we're going to look at a sequence of random variables, zt, and we're going to look at a stochastic update rule for these random variables. And it makes more sense to look at the distribution rather than the random variable. Okay? So now it turns out that if you apply this mixture update, where you sample a next state, starting at x, and sample the reward, and you pass your prediction about the value of the distribution at x prime through this push forward measure, and you take a step in the direction of the measure, then you would converge to e to t. Now, when I say take a step, you should be careful. Well, you can think of this as a sign measure, so you're summing up sign measures, and then you're in some sense guaranteeing that almost surely you're going to converge to e to pi, okay? Where e to pi is a distribution corresponding to the collection. Now, the funny thing about this is that in general, this is not going to be easy parameterizable, right? So in particular, if you keep applying p pi and you have stochasticity, then you're going to have growing support. So there was this notion of a semi-gradient in the previous slide. Now you can't really talk about the semi-gradient of a mixture. Okay. So what can we do? Well, we can actually say, in practice, we won't be able to represent this mixture exactly anyway. So how about we approximate it with a parametric distribution? So we're going to set up our distribution so it's supported on a finite set of atoms, Z1 to Z. Okay. And then we're going to assign probabilities P1 to Pk to these these atoms. Okay. And then what we're going to do is, after applying the Bellman update, the Bellman operator to our distribution, specifically with the sample we've drawn. Okay. So that was a push forward measure before. Now we're going to project that target, if you will, back into the space of distributions that we can actually represent. Okay. So in the previous slide, we were allowing ourselves the complete freedom of representing any distribution. And now I'm going to say, let's think of a projection that would actually allow us to keep things on a finite support. Okay. So it turns out, and I'll show you the projection on the next slide, but it turns out that if you write down things this way, then you will, first of all, still converge to a distribution eta tilde, which isn't too far from e to pi. And in fact, it depends on the largest gap between the elements of your support. Okay. And it also turns out that this update rule, that looks very much like a TD learning rule, but now with distributions with the parametric support, is the semi-gradient of the Kramer loss. And this is work that's ongoing. Nicolas Leroux and I have worked on this, and also Claire Lyle from McGill University. Okay. And so then the nice thing is, well, we know the Kramer loss, the Kramer distance is going to be gamma to the 1/2. Going to induce a gamma to the 1/2 contraction in its operator form, so we can talk about the rate of convergence of this process. Okay.
So this result based on specific definition of projection, right? Based on L2.
I am going to show you the projection just on the next slide. That's right. So all of this is for a yet to be described projection. Okay. I wanted to show it to you. There you go. So how does this projection actually work? Okay. So you're going to start. I'm just going to show it to you for one atom of your target distribution. So what's the target distribution? The target distribution is, I sample the next state, I look at its distribution, and then I squash it and shift it. That's the cartoon picture I showed you before. Okay. If you look at that, what's called T pi z here in red, okay, so the projection step is going to go like this. First of all, we look at the distance. We have Z1 and Z2, two atoms of the actual distribution we can represent. We're going to look at the distance of our target to both of these atoms. And then we're going to assign a proportional fraction of the probability mass at the next state distribution to each of these two supports. Okay? So the closest one will get most of the mass. So that if you're on the atom, then you don't actually do any projection for that particular atom. So then we end up with a new distribution Q1 and Q2, which would be, if you will, you're assigning the mass proportional to the distance. Okay? And that distribution is actually on the same support as it's on Z1 and Z2. We define it to be so. And then we can update to it. So that sort of describes the process of learning. Now, how do we actually make decisions? I haven't talked about this so far, but let's, in expected RL, we have this max operator. Now, of course, once we have distributions, we can't just take the max of a distribution. Okay. So one thing we can do is we can cop out and say, let's take a policy which is greedy with respect to the expectation. Right? With the hope that if we do this, then we might converge to a value distribution which is in some sense optimal. And if you were to define and practice, say, an epsilon greedy policy, then you do the same thing where you act greedily according to the expectation. So I'm going to actually just set this aside for now. We're going to come back to this at the end of the talk. And now I actually want to move into how to take all of this and convert it into something you can run in practice. Maybe before I do, I can take one or two questions. No questions? Okay, good. Atari. Okay. So, of course, I've done a lot of work applying reinforcement learning algorithms to video games, in particular the Atari suite of video games. So this is a collection of 60 games with video input, and where the actions are joystick motions. Okay. And one of the most famous success in that story is DQN, the DQN algorithm, which took a convolutional neural network and then mapped images to actions, okay, and then tried to maximize reward. Okay, so in this setting, the state space becomes all possible configuration of the RAM. The action space would be the joystick motions. The reward function is a score differential from one step to the next, and the transition function is given by the Atari emulator. Okay. And the discount factor is almost always 0.9. Okay. So DQN as an algorithm learned the Q value. How does it look? If you get DQN to play in practice, if you've never seen this game, this is a game called Space Invaders. This is very typical of Atari. You're trying to score points, and if you fail at scoring points, you lose the game. All of these games are episodic in nature. Okay? And what's pretty neat is we can actually, using something as simple as Q learning, we can learn to play these games. Okay? And so this is actually one of our later agents, using a technique called persistent Q learning, playing Space Invaders. And you can see at the top there's a score. Every time that changes, that's the reward that the agent receives.
How do you choose gamma?
Very Eurasian. It's almost folklore now. You should use like. I think
is there any reason for
higher values of gamma has actually led to divergence, and lower values led to less performance. It's one of these many early decisions that have never really been revisited. People have looked at it, and then consistently, of course, find that it's still
so empirical.
empirical.
Are you using like an epsilon UD after that?
And this is with an epsilon UD pulse. Okay, so how do we convert the distributional ideas into an algorithm? Well, the naive thing to do is to say we're going to replace the Q value output by a probability. Okay. So remember, I told you we could parameterize those distributions with a fixed set of atoms. So let's do this. Let's have, say, 51 atoms evenly spaced on a range, in this case, from -10 to 10. Again, empirical choices. And let's parameterize the distribution using a softmax distribution. So the deep network will now output logits with softmax distribution. Okay. And now our job is to make this work, and in particular to make the distribution to distribution update. So the only real difference between these two algorithms is instead of having a squared loss between, like I was showing you earlier, that we would get in Q learning, now you'll have a distributional loss between the next state prediction, that push forward prediction, and then your current guess.
So, I'm sorry.
Yes, of course.
Space of action is how you move it's a one-dimensional thing, how you move
Very good question. So the Atari suite actually has 60 different games. And the space of actions is always the joystick motions. So up, down, left, right, and press the button, and then the cross product of these.
So what you just showed us is just left, right, and
exactly.
pushing the button.
Exactly.
The space
And also don't do anything. So you're allowed to stay still. In the context of this game, I think there's 6 sections. So actually, maybe preempting your thinking, all of these games have a very narrow set of actions.
What about X here, the space of X?
X is, an upper bound in X is a number of possible RAM configurations. And there's, in fact, 128 bytes. So 2 to the 1,000 possible states. Now, in practice, of course, that's not the case. But if you do look at, if you count how many unique screens you would see, it's in the millions. It's in the, you keep seeing new screens as you go along. Now, these states might be unique, but there might be a good mapping, an approximate mapping from images to a value function, which is good enough to play these things. And that's really where we're going to get the traction. Okay, so how does this algorithm work? Well, we're going to want to try to apply this operator, but now in practice. Okay? So same thing, we'll start with now, we have an action in there, so from a statement action, we're going to sample a transition. Okay? And then we're going to compute a sample backup, which would be what we want to learn about. Okay? And as I said before, we can apply this projection to make sure that it's within the support, our 51 atoms, so we can actually learn about this. And now it turns out that the natural thing to do would be to directly minimize one of the losses I was telling you about, like the Wasserstein derived loss, or parameter-derived plots. It turns out that early on in this project, we didn't know how to do this. So instead, we copped out again and just minimized the KL between the projection and the target. And in some sense, there's a good reason to do this because we had a softmax transfer function to map our logits to probabilities, so it might make sense to have a KL set afterwards. Okay. So if you aggregate the performance of that agent across all 60 games, you have a classic metric is to talk about the mean score and the median score. These are percentages because they're in terms of a human evaluator. Okay. And what's quite neat is over time, over about 3 years of development, this started with DQN. DQN had these scores, and then people started adding bells and whistles to get to a point, an algorithm called prioritized dueling, which actually did quite well compared to the original DQN algorithm. And the neat part is when we looked at this distributional algorithm, we stripped away all of this. We just started from DQN and said, what if we change just the learning rule? Okay. We're still acting according to the expectations. We're still being excellent greedy with respect to the expectation. But it actually makes a huge difference. Okay. So we actually beat the state of the art without any of the bells and whistles. And this was incredibly surprising. Okay. So here's a plot. Here's a classic plot. This is a game called Sequest, and you have a learning curve here. This is actually the C51 algorithm. This is the previous best, and you have DQN somewhere in one of these lines below. These are different parameterizations. It was pretty incredible, given again we're just maximizing this expectation. And this is where the question, why does it work better, becomes very relevant. We still don't have to this day, we still don't know exactly what makes this work better. Okay. One thing I have some slides before that. Let me show you one. Yes.
So is this curve sensitive to the choice of atom? You said
it is.
If you make a bad choice of atom, would you have the same incredibly high performance?
That's a very good question. So we did, in fact, these curves here, if you use fewer atoms, and it saturates around 51, and then you can make it work for 101 and 200, but it's about the same performance. There's follow-up work I might or might not have time to talk about, which actually extends this. I had the bound maybe 10 slides ago relating the error from the projection set, and it's in terms of the gap. So the smaller the gap between your atoms, the less error you're going to have. Now, there's another part to this question, which is we actually, in this particular case, we were bounding the value function at -10 and 10, and that's also Haber parameter. But even then, we're still doing quite well. So maybe the other more convincing answer I can give you is this has been reproduced in a number of other settings, and it consistently outperforms. So it's not just empirical choice. Yes?
Are you plotting the total return or the discounted return?
This is total return. Very good question.
So do the discounted returns match, or there's a strict improvement in the discounted returns?
In the predictions, you mean? Or I see.
The discounted returns, because the Bellman,
Right.
the vanilla Bellman operator is maximizing the discounted return.
That's right.
So in principle, one should not be able to beat that.
So we're also using a discount factor.
Yes,
so,
right, but are you doing, in the discounted returns, do the two algorithms have similar performance?
That's a very good question. I don't have the answer for you. I would imagine that that's still true. That I don't see why it wouldn't be true that the algorithm would still be better with discount. Yes.
So this shows this one game, Sequest. Did you find similar improvements for every single game, or were there some games where it seems like previous things already do really, really well?
Don't have full details. It's in the paper. I think, actually, I have in one number here, which was we were better than DQN on 44, and better for some notion better. So I don't think there's many games, if any, where it was a significant decrease in performance. Oh, actually, it was 15 or 45.
So what's the HB column there?
It's better than the human.
Oh.
Better than the human. Let me show you these two videos very quickly. I'll skip maybe the top one to just show you. Oops. I guess I've lost the top one, so I'll show you the bottom one anyway. The bottom one is the value distribution, okay, for my predicted return. So we have 51 predictions. In this case, it turns out for most of the games, we don't use the negative parts. I'm just showing you the positive part of this prediction. And that's over time as the agent is playing the game. You actually have multiple curves overlaid on top of each other. Each of them is a separate action. Okay? And in fact, the agent is making choices based on tiny, minute differences in expectation. That's why you can barely see that these guys are overlapping. But one thing that's common is that when the agent might lose a life or lose a game, for example, when the invaders get to the bottom of the screen, then you see this bimodality appear in the prediction. So something that you wouldn't get if you would just predict the expectation. But now you see there's a probability of getting a 0 or 1. And that's very new to this kind of method, that you can get this rich prediction. In a very informal sense, the people's insights is that this is what's making the difference. And it's incredibly informal. Okay, so just to sort of point out, as I was saying, this has actually been reproduced. So by now, there's been a number of papers that have taken this technique, applied it to new domains, or improved on it. There was this paper by some folks at DeepMind where they took all these bells and whistles and now brought them back in and found that the distributional learning approach was actually one of the main factors in performance. So that's actually very exciting. I think my favorite is somebody, Felix Yu, who read the paper, as is common in this age of deep learning, read the paper, got very excited about the idea, re-implemented it, applied it to a new domain, in this case a game called HisZoom, applied it to a new domain, and emailed me and said, oh hey, this actually works better in this domain too. So best proof of concept you can hope for, right? So this was quite neat. Okay. I'm going to show you, maybe I'll skip over this. No, I'll show this. This is very quick. So this is also work from some folks at DeepMind. This is an agent learning to parkour in a very funny way. And one thing you'll see is it's trying to dodge these walls, and sometimes it succeeds, and sometimes it doesn't. Right? And this is a learned policy, so the policy is not really changing at this point. Okay. So if you actually look at this agent, okay, and plot again its prediction of the value distribution over time, then what you're going to see is, watch out what happens when it gets close to a wall. Right? You can clearly see that there's two modes. Am I going to make it? I don't make it, or I won't make it, but I can predict both of these events. And that's actually very interesting because all of these, both Atari and these simulated environments are all deterministic. So if you didn't have any sources of noise or approximation, you should really converge to the best thing. Right? But somehow we're keeping that residual stochasticity in there, and that's a big mystery. So let me go back now to this question of Bellemare and Wasserstein metrics. Okay.
So just to, so where is this residual stochasticity coming from?
Very good question.
Oh, you don't know?
I don't know.
See.
I mean, there's many hypotheses. I'll tell you about one of them at the very end of the talk. There's some stochasticity in the agent's behavior, but it shouldn't be enough to give rise to failures like this. Now, the approximation is another one. I'm getting ahead of myself. So, we've talked about these LP metrics, the Cron distance in particular. Okay. So what about the Wasserstein metrics? If they're better, can we use them? It turns out that you can't do gradient descent with a sample Wasserstein loss. We actually spent quite a bit of time looking at this. So if you just sample the next state and define the same target distribution we're talking about and try to do gradient descent with the Wasserstein loss, you'll get the wrong answer. And it was very frustrating. So we couldn't use it out of the box. Okay. But my co-author, Will Dabney, was very persistent and said, what if we rethink what we're doing right now? So right now we're predicting a distribution with 51 atoms with varying probabilities, okay? That has issues, in particular because it's not Wasserstein friendly. We can't do SGP with it. Now what if instead we took that softmax distribution and instead we fixed the probabilities to be uniform and instead just parameterize the support? So now we're going to allow our distribution to vary, but only in the support, not in the probabilities we attach to these items. Okay. So the way to think about this is if you have a CDF, you could either parameterize its probabilities and keep the support fixed, like we did, or parameterize the support and keep the probabilities fixed. Okay. So you can think of it as doing the transpose of the C51. It turns out even if you do this, SGP is going to fail. So that's still, stochastic gradient descent is still not going to work. But a different approach called quantile regression is actually going to give you what you want. So if you parameterize your distribution so as to keep the probabilities fixed and uniform, basically if you try to learn the quantiles of your distribution, then you can do this. And Will has this very nice result that shows that if you do quantile regression in a reinforcement learning setting, then you get a contraction mapping. So we're using a different algorithm, we can actually get traction in the Russian settings. And it turns out, of course, you apply it to Atari, and it works even better. So there's reasons to believe that this is a very promising avenue. One natural reason is you have a higher contraction, you have a smaller discount factor, smaller contraction modulus. So that should help you. Okay. So quite neat work. Now, I want to just close on coming back in the theory and talking about this question of control and finding the optimal value distribution. Okay. Because that's where the distributional approach to reinforcement learning is going to be different from what we have in the expected case. Okay. So in Q-learning, you have, as I said, you have a TD error, which is derived from taking the maximum value of the next state. Okay? And we can write the operator, and finally we can say that this converges because we have a contraction in supreme. Okay. So this is all tabular, no approximation. Now I showed you this slide earlier, and I said, well, that's great. We can define the distributional optimality operator to be T pi for some pi greedy with respect to my expectation. Now there might be multiple greedy policies. So you have a unique optimal value function, but you might still be able to say go left or go right, and they have the same expected value. Okay. So it turns out that actually throws a wrench in the works. So it turns out that if you analyze the property of the control, the optimality operator, then first of all, in general, it's not a contraction. So once you take the equivalent of you take the greedy policy, you are no longer guaranteed to have a contraction happening. Second, if you're not careful in how you define your mapping, how you choose your greedy policy, then you might not even have a fixed point for that operator. Okay. And then third, even if you do have a fixed point, if you repeatedly apply this operator to get a sequence ZK, you might not actually converge to Z star. So you could have a fixed point, but you don't converge to it. And in fact, the best result we could find was that if you repeatedly apply this optimality operator in the distributional case, you're going to converge to a non-stationary optimal value distribution, which means it's the value distribution of a non-stationary policy where you're allowing yourself to change your mind at every step. And in fact, this hasn't been published, but if you now do a mixture update with the step size, then you step away even from non-stationary policies into non-Markov policies, where you're making a choice at the beginning of time which sequence of non-stationary policy will I use. So it's a bit surprising. So let me show you the example very quickly. Yes.
One more slide. So this is the operator on this is binary.
This is
not binary.
This is infinite arising with a discount. So the issue comes from your that choice. That you can choose whatever greedy policy you want. So as soon as you have two optimal actions, or even if you think that there's two actions that are optimal, and you update them, then you get a new problem. Let me show you the example very quickly. In this example, it's a very, very simple example. You have a state x1, and you're going to transition to state x2 and then choose action a1 or a2. a1 gives you a reward of 0, and a2 is actually the unique optimal action, gives you a reward of epsilon plus or minus 1, where equal to infinity, where epsilon is 1. And you can, so Z star here is, of course, you go in x2 and you choose action a2. So this has distribution epsilon plus or minus 1, and this guy also has distribution epsilon plus or minus 1. Now, if you start very close to Z star, say almost the same, but you think that action A2 actually has slightly less value, flip the sign here. Then when you back up, when you make your backup from x2 to x1, you're of course going to choose action A1 because it has higher expected value. Okay. So you do your backup, and then you're going to end up with a new distribution where the distribution at x1 is now the distribution that used to be at x2. So in this case, in the undiscounted case. So this is now 0. And it turns out that it's not too hard to show that, of course, you can always make tz further from z star than z was. So you've actually stepped away from z star with a single application of this operator. So here's the final picture of release. If you look at expected RL, in supremum norm, we have this beautiful picture where we spiral and converge towards Q star. And then we can guarantee convergence. Now, when you move to the distributional case, we're not necessarily going to converge at the same rate. And also, even when we do converge, we don't know that we're going to converge at this. Okay? So I certainly think that there's some unanswered questions here. So very briefly, I think that's actually a very exciting research direction because in reinforcement learning, there's multiple aspects. There's a prediction, there's modeling tools, learning rule, and everything sort of fell from the value function. Okay? And then by replacing this reinforcement learning by distributional reinforcement learning, then suddenly we can start looking at all these other questions, and we're finding all kinds of surprising answers everywhere. Okay, so I'm going to leave on that question, when does it work better? We don't know. I think right now the odds are that it mostly works because of decluttering, which I think is very interesting in the context of this session.
What is it here is distributional versus distribution?
Exactly. So why are we seeing this performance gap and consistently seeing the performance gap? And it looks like the answer is that it helps you find a better deep network to approximate to your distribution. So I'm going to end here with a shout out to my collaborators, Will Dabney especially, who pioneered this work with me. Thank you. I think we have time for one question.
So in RL, you're usually trying to maximize an expectation, but I can imagine you want to control the variance sometimes. This is going to be applicable?
It would be. There's actually a lot of work that's been done both in operations research and also in reinforcement learning on exactly that question. What's surprising here, we came at it from a very different angle of saying, what if you don't actually care about variance? And that's a very surprising thing to me. Now, of course, now you have these tools. We saw, for example, the visualization of the agent that could tell that there was a risky situation. How could he deal with this? It turns out I haven't seen at least in a deep reinforcement context, I haven't seen a clear win yet. But I think that would be very interesting to look at.
Is there a try without the approximation part, without the network?
Not as much as we should. That's happening now. So now, I think the short answer is we have results. If I couple, so if I basically have an agent that learns the expected value and an agent that learns the distribution, and I couple them in the sense that I make them follow exactly the same paths, then there's no. I can show you that there's mathematically no difference, right? Both in the evaluation case and now by transition to the control case. So we know this in the evaluation case should make sense. Gary.
Maybe in the tabular case you can use this somehow to do some more clever exploration, so to say, because I guess you still combine the absolute Greek. But now that you have a distribution, maybe you can predict like quantile instead of something.
So that's a good point. Now the caveat is this distribution is not about uncertainty.
Yeah, right.
Right. So you're not assuming that you know or don't know your parameter. You're actually learning that parameter. I don't know that it would be principled to try to explore based on additional moments that don't reflect uncertainty. But that would be interesting to find out if you can. There was maybe a nuance.
So have you ever tried to see if the distribution that is predicted by the architecture is actually the distribution of the term that you observe? Because I guess in the expected case, sometimes you predict something that is very biased, but still you perform well. Here it is possible that your distribution prediction is maybe not calibrated, but still you get something out of it.
Again, I agree with you. That's an experiment we should do. I haven't seen it done. Maybe we should call it time. One more question.
Tiny one. So you say, why does it work better? It works better, but you're computing a distribution instead of an expectation. So imagine it's harder, right? You need more computing power, more time. So does it really work better?
I see.
It's the amount of resources that they have.
So the very practical answer is, once you have a GPU and distributed resources, the cost is actually negligible, surprisingly.
I'm sorry?
But it's true that if you did everything sequentially, then you would have. That's a very good point. All of this now is done in the context of having a GPU where parallel operations are cheap. And so, in fact, the distribution, everything that we do here is matrix multiplication, which is because we have finite distributions.
Okay, let's thank Marc again.